In this video, we're going to begin to talk about Chapter 7, which is about sampling distributions. As I mentioned previously, at some time during the course of this course, I mentioned that sampling distributions are extremely important. Okay, there's something extremely important coming up, and it is sampling distributions or a sampling distribution. And so this idea or this mathematical structure or probabilistic structure that we're going to build up here in Chapter 7 is something that we're going to use throughout the rest of this course to do almost anything that we do from now on will involve sampling distributions. So first we need to talk about what is a sampling distribution. Then we'll talk about the sampling distribution for the sample proportion and a sampling distribution for the sample mean. Okay. So the sampling distribution of a statistic is the probability distribution that specifies probabilities for the possible values that a statistic can take on. So what that means, or important implications here, is that before we were just talking about probability distributions about a random phenomena, any old random phenomena. But sampling distributions talk about or are about statistics, and a statistic is any summarization of data. So the big shift between Chapter 6 and Chapter 7 is that now we're taking data. And so we have some situation that is a random phenomena, but we're taking data from some population. Okay, so we're taking data from some population, and then we're building a sampling distribution about that statistic that we take. Okay, and you may say, well, data is not random. We take it and there it is, and that is sort of correct, but we're not talking about the data itself. We're talking about the summary of data. So whenever I take a sample from my population, so the population could be heights of people. Okay, so the distribution of heights of people maybe is approximately normal, but it doesn't really matter what kind of distribution it is. Okay, we have some distribution of heights, and I might take a random sample of maybe 25 people and look at their heights. Okay, and so I can take that data and then calculate the mean. If I'm looking for the mean height of maybe all people, I can take a sample of 25 and then I calculate the mean height of those people. Now if I take another sample of another 25 people and calculate that mean, that summary, that mean is going to be different for every sample that I take, and thus it's random. Okay, and so a sampling distribution describes the randomness or the variability in the statistic that we're interested in. Okay, so the big takeaway here is we're now taking data. Okay, we're not in a fully sort of theoretical land. We now have some data to work with. So here's an example that'll be better thought out than the one I just gave. Suppose I flip a coin 1,000 times, and I'm looking for the sampling distribution for the sample proportion of heads. Okay, so when I flip a coin 1,000 times, and I look for the proportion of heads, okay, every time I take 1,000 coin flips, I'm going to get a different proportion. Okay, I might get the same one a couple of times, but it's not every time that I get the same number. And so the sampling distribution shows us how likely those different possibilities are. Okay, so what kind of distribution does that look like? That's sort of the question that we're interested in. A sampling distribution informs us of how close a statistic falls to a parameter. Okay, and so we'll get to that discussion a little later on. So here's an applet that I'm going to go to very quickly. okay, that shows the idea of a sampling distribution. Okay, this is going to be for the sampling distribution of a sample mean, not a proportion, but we'll get to why those aren't really that different, a proportion and a mean. They're actually, a proportion is actually a special type of mean. But anyway, so here is, and hopefully you can see this, maybe I can zoom in a little bit here. So I have some parent population. So maybe these are the distribution of heights of people. Okay, it's from 0 to 32, but that really doesn't matter. Here's my parent population. And maybe my population is normal. Okay, so what I'm going to do is then take a sample of size 5, okay, and then see what I take a sample of size 5 and then take the mean of that data. So watch this, 1, 2, 3, 4, 5, and then it finds the mean of that data, okay, and I'm interested in the distribution of means down here. Okay, so I can do that again and again, and you see every time it's different. Okay, and maybe I can do this 5 times. Okay, there's 5 times, and then I can do it 10,000 times. Okay, and lo and behold, if you look here, you can see that here is a distribution of the means. They're not always the same, but in fact they look, something interesting happens here, and it looks normal. Okay, and I'll revisit this app later, but in fact you can start with any parent population. So here's a skewed population. Okay, and maybe I'll do a mean of 20 points now. If I take a bunch of samples and you look here, you'll see that this distribution again is not, it's not one number, but if you look here, this distribution looks awfully normal. Okay, and so this is something special that we'll see in just a little bit. But anyway, we're back here, sampling distribution. Let's first talk about the sampling distribution of a sample proportion. Okay, so if you remember, the sample proportion is p hat. Okay, so p with a hat over it is what I say the sample proportion on. It depends on the sample size n. Okay, as we saw earlier in the virtual stat lab thing that I just showed, the sampling distribution of really anything, any parent population, starts to look normal if I move n up high enough. Okay, so it's actually, in fact, the case. So formally, under certain conditions, the sampling distribution of p hat, which is the sample proportion, is approximately normal. So specifically, p hat, the distribution of p hat looks like this. Okay, so there's a lot of new stuff here. Instead of 1 tilde, I now have 2 tildes. Okay, so 2 tildes over each other. That means approximately, is distributed approximately. So 1 tilde is actually, okay, 2 is approximately. You don't really need to worry about the difference between 1 and 2 tildes. Okay, they basically say the same thing. The distribution of p hat is approximately normal with a mean of p and a standard deviation of the square root of p times 1 minus p divided by n. Okay, so square root of p times 1 minus p divided by n. So that's the standard deviation. Now this is only true if certain conditions are met. Okay, and this is going to be extremely important throughout everything that we do past this. Everything is conditional on some conditions being met. The conditions that need to be met in this case are that n times p and n times 1 minus p are greater than or equal to 15. Okay? Now, n times p is really the expected number of successes, and n times 1 minus p is the expected number of failures. Okay? And we need both of them to be greater than or equal to 15 in order to ensure convergence, is what I write here. If it's lower than that, okay, if n times p or n times 1 minus p are lower than that, it is possible that the distribution won't look normal. Okay, it isn't quite normal. Maybe it's a little skewed to one direction or the other. But if n times p is greater than or equal to 15 and n times 1 minus p is greater than or equal to 15, then we can safely assume that p hat is approximately normal. Okay? Now, one thing that I do want to say, or one extra thing that I want to say, is that being greater than or equal to 15, these two conditions aren't like mathematically proven to be true. These are more like recommendations. So I've taught this course out of a number of different books. Some of them say that n times p, these two things need to be greater than or equal to 5 instead of 15. Other books have said 10. Okay, this one says 15. So there are different rules. They're shown to empirically work, but they're not mathematically proven. Okay, so here's an example. Okay, at a university, 60% of the 7,400 students are female. Okay, the student newspaper reports a survey of a random sample of 50 students about various topics. Okay, so I take a survey of 50 students about various topics, and I'm interested in one, what's the sampling distribution of p hat? And then two, I ask a probability question. What's the probability that I would actually see at most 26 females out of 50 respondents? So first we need to answer the question, what's the sampling distribution of p hat? So essentially I'm looking for what I just wrote on the last page. But I need to check first if the sampling distribution of, if I can say it's normal. Okay? And to do that, I need to take n times p and n times 1 minus p. So n is 50 times the probability of being a female. Okay, so really what I should say here and that I forgot to is that I'm counting, or I'm interested in the proportion of respondents who were female. Okay, so that's what p is. P hat is the proportion of respondents who were female in the sample. And so I need to take 50 times 0.6 to get n times p. That's 30. Okay, which is greater than 15, so I'm good there. And then I need to do 50 times 1 minus p, which is 0.4, and 50 times 0.4 is 20. Both are greater than 15, and so I can assume that p hat has a normal distribution with a mean of p, which is 0.6, and a standard deviation of the square root of 0.6 times 0.4 divided by 50. Okay. Now I know me saying this is probably not helping. I will send out this completed and put it on the content page of D2L afterwards. So I can't write on it right now, but I will after this video. Okay, so now I have the sampling distribution of p hat. And then I ask a probability question. What's the probability that I would actually see at most 26 out of 50 respondents? Okay. So I'm looking for a probability about p hat, okay, of which I have the distribution above. So really what I'm asking is just a normal distribution question, which we saw from chapter 6. But now, instead of some number that I throw out, I'm asking for the probability that p hat would be at most 26 out of 50. Okay, so the probability I'm looking specifically for, the probability that p hat is less than or equal to 26 divided by 50. Okay, and so you just substitute in mean and standard deviation in Minitab, and then it should shoot out a number. Okay, so you of course have to plug in 26 out of 50 as well for your actual number. Okay, so here's a your turn. Suppose it's known that 25% of dog owners in Shippensburg dress up their dogs for Halloween. Now suppose that I randomly select 50 dogs from owners, 50 dog/owner pairs from Shippensburg on Halloween, and the question I'm asking is 1, what's the sampling distribution of p hat, and then 2, what's the probability that I would actually see at least 10 dogs dressed up on Halloween.